Hello, and welcome to this lesson in discrete mathematics, discrete structures. Today we're going to look at the method of proof by induction. I'm going to look at the steps in doing it. It is fairly straightforward. Every time the steps are the same. It's often used to prove that a formula is true. So, for example, the sum of the first n integers is from 1 to n, adding up n, so the sum of the first n integers is written there in sigma notation. Rather than having to keep adding, you could just take the value that you want to stop with and multiply times one more than that and divide by 2. And that will always give you the sum of the first n integers. So how do we know that's true? Well, the first thing you do is you check. So this is for n, because of the way the formula is written here, this is for n greater than or equal to 1, because of the way the sigma notation is indexed. So first thing you do is you always show that the first term will be true. Like if I only have one term, I show this. So if I goes from 1 to 1, what do I, from 1 to 1, what do I get? I would get 1, because the value of n would be 1. So I'm trying to show that the formula will also give me 1. So I plug in n is 1, and n is 1 here. 1 times 1 plus 1 divided by 2. If you look at the formula, that's what I'm doing right here. And when I do that, using proper order of operations, I get 1 times 2 divided by 2 is 1. So that's my first step, and that works, so I can continue. The next step confuses students more than it needs to. It looks just like a change of variable, but you're just saying, so for some number k, I'm going to show that if I find p of k and then add to it the k plus first term, I get the same as if I did the formula for p of k plus 1. So this is what you call your inductive hypothesis. So you write out what you're doing. You're adding 1 plus 2. So really, 1 plus 2 plus 3, instead of n, it's a k, but all the way up to k. And it's helpful to write it out this way rather than sigma notation so you see what you're doing. And you're going to assume that this is true, that when I add that up, this is going to be k times k plus 1 over 2. So you're assuming the formula is true. That's the inductive hypothesis. By induction, you just assume what you're proving is true here, and then you're going to use that. You're going to find p of k, and then you're going to add what would be the k plus first term. So if I go one more term than this, the next term would be k plus 1. And then you're going to do the formula for p of k plus 1. And you're going to show it's the same as if you do the formula of p of k plus the k plus first term. Now for this one, that's fairly simple because the k plus first term is just k plus 1. But if my sequence involves squaring, then it would have to be k plus 1 squared I would add. And you have to be careful that you're following the formula you're given. So I'm just adding the next number. K plus 1 will be the next number, as you'll see in a moment. So all of this is typed out, but I'm trying to highlight what we do. Now, we want to prove that the formula holds. So this is p of k plus 1. We want to prove that that's the same is finding p of k, which would be the sum of the first k terms, and then adding the next term, which is k plus 1. If I go add one more number up, I'm adding the next number higher. So you write out this is p of k plus the next term. It won't always be k plus 1. If you're doing something different than just adding the number, if you're squaring things, you'll be squaring that next to get the next term. And you want to show that that comes out the same as this. You're going to need some algebra. This is the only difficult part of this, is you have to do some algebra with some fractions, and I'll remind you of that in this video. And I also will do another video with a couple of examples that you can try, and the steps are written out. So what I have here is I need to add, I'm going to change my pen here. I need to add these two terms. Well, I have a fraction over 2, so in order to write k plus 1 as a fraction over 2, I have to put a 2 in the top and a 2 in the bottom. Anytime you have a fraction plus a number whose denominator is 1, so you say, well, it doesn't look like a fraction, it still is rational. The way you deal with adding them or subtracting them is you take whatever this denominator is and you put it on the top and on the bottom in front of what you're expression was. So I've done that. So now that I have two fractions with the same denominators, I can just add the tops. That's what I did. There's the top of the first one. There's the top of the second one. Now I can multiply through, but it's easy, and this requires a lot of factoring. And if you multiply through and then try to factor, it's way harder than what I'm about to show you. Look at this. I have a k times a k plus 1 plus a 2 times a k plus 1. K plus 1 is a common factor of the top. So I remove the k plus 1 as a common factor, and what I'm left with is the k and the 2. So this is k plus 1 times k plus 2 over 2, which indeed was what I was trying to prove. So my proof is complete. The hardest part of that step is doing the algebra. Sometimes it's a little tricky to make sure you write down the right term, right expression for the next term. Here it was simple because we were just adding the next integer. So it simply was k plus 1 was the next term. But sometimes you'll have to put that within a function. So you will see that in the other two examples I do in the other video. Thank you for joining me, and check for the video on examples also.